Okay, so if you remember, the last thing that I was talking about was the notion of a subset, yes? So assume that we have two sets, one of them is A, the other one is B. We say that A is a subset of B and use this symbol. If and only if what happens, every element X that I see, if that element is in A, then that element is also in B, yes? That is the meaning of a set being a subset of another set. For example, if I have a set A, which is 1 and 2, and if I have a set B, which is 3, 2, 5, and 1, then I would say that A is a subset of B. Yes? So why is that the case? Because whatever I see inside A I see two elements. One of them is 1, the other one is 2, and every one of these elements is also inside B. Yes, it's a member of B. 1 is in A, I can also find it in B. 2 is in A, I can also find it here in B. So I would say that A is a subset of B. Of course, you can immediately see that B is not a subset of A. Yes? If I ask you, why do you say that B is not a subset of A? You would say, because I can find at least one element in B which is not in A. But of course, here you have more than one element with that property. You can say that I can see 3 in B, which is not in A. That's enough for telling that B is not a subset of A. But of course, there is also 5 in B, which is not in A. So if you want to draw a Venn diagram representing being subset, so do you remember we did it before? So let me take this one as the universal set. And then I have a set. So for example, here, let me consider this, I don't know, set B, and let me draw a little bit a smaller set inside that one, and I call it A. Here I would say that this set A is a subset of B. Okay, so this diagram, so let me also write this as the universal set. This rectangle is usually used for the universal set. So I would say that this diagram represents A being a subset of B. And then if you remember, I also talked a little bit about the analogy between this symbol between numbers and this symbol between sets. There are some analogies between these two, but you shouldn't actually answer all these questions related to this using this analogy. Okay, so the main difference, I will tell you about some similarities, but the main difference between this relation between two sets and this relation between two numbers. Do you remember what I told you before? There is a fundamental difference between this relation for two sets and between this relation for and this relation for two numbers. Anyone remember what I said before?
Is it the sizes?
Is it what?
Is it the sizes? So
Uh,
the if you take the size of each of the sets, then they become the same symbol.
no, I would say at least I don't understand what you mean. No, that was not what I meant. There is a fundamental difference because somehow, by the way, if I have these kinds of relations, they are ordering relations. Yes, ordering relations. It means that using this relation, I can order the elements of my set somehow. For example, if I give you a bunch of numbers, 1, 2, 5, 10, square root of 3, you can use this relation to organize them, to order them in somehow here. Yes, so you can say 1 is less than or equal to square root of 3 is less than or equal to 2 is less than or equal to 5 is less than or equal to 10. So you see, I am ordering my set in some way. I say that 1 comes first in this relation, square root of 3 comes second, 2 comes later, 5, and then 10. Okay, so this is an order. It is called the total order. But there is a difference between this relation between two sets and this relation between two numbers. Can you point it out again if you remember something? Between any two numbers that you can choose, there is this relation between them in one direction or the other. Yes. So choose two numbers, whatever you like. For example, 5/10, and then you can choose square root of 3. So then either this relation is true or the other way around is true. Okay, this is always the case. If I choose two numbers, two real numbers, either if I choose two real numbers A and B, either A is less than or equal to B, or if it is not, definitely B has to be smaller than or equal to A. It is not possible that I do not have this simultaneously, I do not have this. But in sets, using this relation, this can happen. If I choose two random sets, there is no guarantee that either the first one should be a subset of the second one, or the second one should be a subset of the first one. This is the main difference. Yes?
What happens if one of the numbers is a complex number? Can you still order them?
No, that you are right. Complex numbers are not ordered fields. Yes, I was a little bit careless because usually in high school when I talk about numbers, I always consider real numbers. Yes, you are right. If we have two complex numbers, that field is also not an ordered field. Yes. So forget about the complex numbers, but the real numbers, this relation is an order, total order relation on the set R, on the set of real numbers. So it means that if I consider this relation, I can write them in order. I can write the elements. I can arrange them in a organized way from the smaller number to the bigger number if I have a bunch of numbers from R. Okay, but this is not happening for sets. It's clear. We did it before. Can you give me an example in which none of them is true? This is false. This is also false. For numbers, this cannot happen. You cannot give me two numbers so that this is false, this is also false. For numbers, this cannot happen. For numbers, either this one is true or that one is true, or actually both of them if A and B are the same numbers. You cannot present two numbers for me so that both of them are simultaneously false. But for sets, this can happen. You can immediately give me two sets for which this one is false, this one is also false. Yes? Can you cook up an example? It's very simple, isn't it? You don't need to make very hard examples. So I can say that A is equal to the singleton. Singleton, do you remember, is a set with cardinality 1. I'm just using these words because I want to refresh your memory. Cardinality is a big name for a very simple thing here, at least in the high school level, and that's the number of elements in your set. So the cardinality, do you remember? Let me just review these. The cardinality symbol is just similar to the absolute value symbol, but when you see inside it, it's a set, it means it's cardinality, it means that I need to consider the number of elements here. And you see that the cardinality of this set is equal to 1. And I told you that there is a name for it. If the cardinality is 1, that is called a singleton. That set is called a singleton set. A singleton, okay? And let me consider another singleton, but this time let me put 2 inside it. If I again ask you what is cardinality of B, it's just 1. There is nothing related to cardinality here. I'm just talking about these words so that you remember these things. But now let me ask you, do you think that this is true or false? A is a subset of B.
False.
It's false, yes, because you find an element here, say 1, which you cannot find it in the other set. So this is false. What about this one? B is a subset of A.
Also false.
This is also false. So you see, there are very examples in the set, in the world of sets, that both of them are wrong. So this, if you study in mathematics, you will see that even computer science, I think they will talk about these things. So this will called a partial ordering. So it is some kind of order. For example, here I can say if I want to organize sets a little bit, they are somehow organized a little bit because I can compare these two sets. I would say this set is inside B, or is contained in B, and B contains A, or A is a subset of B. But for some other sets, the comparison is not possible. Okay, so that's one main difference between this relation among sets and something somehow similar to it in the world of numbers. Okay, now let me state a theorem. So that's an important one. It's not mentioned probably exactly in this way in the book, but these are the things that is mentioned in the book here and there. Okay, so I would say theorem. There are many different parts for this. So let me write part 1. Every set is a subset of itself. Okay, so it doesn't matter. If I choose a random set, I can be sure about this fact that A is a subset of itself. So it doesn't matter which set I choose, it's always a subset of itself. And the answer is clear why this is. So let me write all of them, and then we can talk a little bit about why these are true. Okay. What is the relation of any set with the universal set? Can you cook up a statement for subset, a set, and the universal set?
Is it that every set is a subset of the universal set?
Exactly. I will just write exactly that sentence. So every set is a subset of the universal set. So what does it mean? It means that if I choose any random set, and then U is my universal set, I'm completely sure that this happens. By the way, let me write this. Don't get confused. Can I say that every set belongs to itself?
Yes. No, absolutely not. No, sorry.
Absolutely not. Actually, there is an axiom called regularity axiom in axiomatic set theory to prevent this. No, actually, there is no set belonging to itself. Okay. But I don't want to talk about that, so that don't get confused. So every set is a subset of itself. For example, let me talk a little bit here. So if I say that A is this one, and I say that A is a subset of A, you have to agree with this one, because what's the meaning of being subset? It means that whatever you find as an element in the left-hand side, it's also an element on the right-hand side. So that's true. Whatever you find in the only thing that you find on the left hand side in the left hand side is 1, and definitely this is also inside the right hand side. So this is true for this set at least. But if I take this one to be this one, if I want to have a set that has A as its element, it should be something like this. Okay, it might have other elements as well, I don't know, but what is clear, this should contain the element of this set. And then you see that this set is no longer itself. So don't get confused. I still want to understand the difference between this relation and this relation. Okay, so this is not true, okay?
But Mr. Babak, can't you define a recursive set? Or is that
How?
against the rules? I mean, the set A equals and then brackets and then A.
No, but anyway, no, there is no set belonging to itself.
Okay, but
the reason is clear, more or less, the same idea, but of course this is an axiom in set theory which prevents this, but the idea is clear because whenever you want to open a set, you need to put a extra curly brackets around, you know, and then if you want to put the set inside, then this set and the previous set are no longer the same. Do you understand what I mean? So if you have this set 1, if I ask you, tell me a set, so if this is A, I want to tell you that A does not belong to A. This is clear, yes? Does A belong to A? Because A is this set. If you say yes, A belongs to A, it means that inside A, you should see the whole package, but you don't see it. What you see inside A, there is only one. If I ask you, give me an example which has A as its element, then you would say, for example, this one. But I cannot call this one again A. This is not A anymore, yes? The element inside A is just single 1. The element inside this set is the set containing 1. They are not the same. Okay, and then this is the same. You are not allowed to write A belongs to A. Okay, so don't write that, but you are allowed to write this. So that's make sure that you understand this. Okay, the universal set is one extreme case. Another extreme case is, can you guess what? If I want to write another statement for number 3.
that no set is a subset of nil or the empty set.
No, unfortunately, there is a set which is subset.
Except itself.
Yes, itself, because this would be a violation of the first rule then, because we agreed that every set is a subset of itself, including the empty set. So that is not the correct extreme. The correct extreme, which is a little bit strange, but we want to talk about this, is that the empty set is a subset of every set. This seems a little bit odd, but this is always the case. So if I choose a random set called A, then I am sure that the empty set is a subset of that. I will come back and talk about this. This is also discussed in the book. Another property that I want you to know, and this is the similarity. This is the similarity between this relation and this relation. Yes. Do you see any similarity before I express it? And actually, there are two similarities. One of them is a statement number 1, yes? Can I write A is smaller than A without knowing what A is, as if A is a number?
Yes.
Yeah, so that is a similarity. So when you pick a random number, I am completely sure that A is less than or equal to A, if A is a number. And the same is true. If I just pick a random set, then I am completely sure that A is a subset of itself. So this is one similarity. Okay? Can you see another similarity between this relation for numbers and this relation for sets? That would be the statement that I want to write as the next statement. Okay, let me give you some hints. What happens if I draw, you see in the picture, I draw a bigger set here, C. Is this a good hint for you now?
Does it have to do with if A is a set of B and B is a set of C, then A is a set of C?
Yes,
Subset
but you
of, yeah, not a
subset.
set of. Yeah.
Subset, exactly. And do you agree that this is a similarity between this relation for sets and that relation for numbers? Because we say that if A is less than or equal to B in numbers, and simultaneously B as a number is smaller than or equal to another number C, what is the conclusion? The conclusion is A is less than or equal to C. This is called transitivity. Okay, so this is also true for the sets. So I would say that being subset being a subset is a transitive relation. What does it mean? Namely, if A, B, and C are sets such that, as Alex said, A is a subset of B and B itself is a subset of C, then A is a subset of C. Okay. And the last one that we'll talk about it later. So number 5, it's not that clear yet. So, but the number of subsets of a set is clear if the set is finite. So I would say that if A is a set of cardinality n, then the number of its subsets, I don't know, do you have any guess? So let me write this number later, okay? I will give you examples and then we come back later. But to understand why this is true, you need to wait a little bit when we talk about combinatorics, okay?
Isn't it an exclamation mark?
N factorial, no.
Yeah, it's not, okay.
No, it's not that. But we will come back to this later. Just I want to talk about this here because I want you to know about this information, but this will come a little bit later in this chapter. But when I am talking about subsets, it's better to have them in one place. So we can talk about the proof of all of them except probably the last one. Okay, so let us think why they are true. So if I want to do the proof, why this is the case? Number 1, why do you think this should be true? Every set is a subset of itself. So if I want to write it rigorously, I would say that let A be any set or be a set. We prove that A is a subset of itself. How should I prove this? So you see here, this statement is here. For the people who did mathematics specialization, you see, I just want to write it. Okay, so it becomes for all x belongs to A, then x belongs to A. But these are the same statements. So either they are both true, so the statement becomes true, or they are both false, this conditional again becomes true. This is one way. But let us go back so in a way that everyone can understand that. So we prove that A is a subset of A. How should we prove this? It's very clear, isn't it? Because it means that whatever, so this relation is true if and only if whatever is an element of the left-hand side is also an element of the right-hand side. Because now the left-hand side and the right-hand sides are exactly the same sets. So if something is in A, it's definitely in A. And then I am done, as simple as that. Yes, so we prove that this. So to do this, let X be an element of the left-hand side set, which is what is A. Then clearly X is also an element of the right-hand side set, which is again A itself. Yeah, it's so trivial that even writing it seems a little bit stupid, but I hope that you understand what's going on. So every set is a subset of itself. The second one is true by definition, because when I talked about the universal set, I told that the universal set is defined to be a set such that the members of other sets are coming from the universal set. So number two has nothing, it's just a definition of the universal set. I wanted to make it complete, so I put this as a statement here. That's not a theorem, actually. That's the definition of the universal set. But the only interesting part is part 3 probably here, which is a little bit confusing. So the empty set is a subset of every set. So can you give me why? Can you give me a statement why this should be true? So let me go to the next page and let me write number 3. Let A be a set. We prove that empty set is a subset of A. How do you think I should prove this? Okay, let us
definition of a subset and then seeing what it evaluates to. Oh, sorry.
The definition seems, I don't know if you can cook up yourself, but let me review this. Let me review this here. So let me change my color. Can you translate this in this kind of symbols? Here, when we say A is a subset of B, it means that every X such that if X belongs to A, then X belongs to B. In other words, every element in the left-hand side is also an element on the right-hand side. But when you say B is not a subset of A, what is the meaning? It means that you can find something in the left-hand side, but that element is not in the right-hand side. That is the meaning, yes, when you say B is not a subset of A. So the proof here is also a similar proof. It's called proof by contradiction. So I would say, assume that this is not the case. Assume that this is not the case. And MT is not, the empty set is not a subset of A. Then this means that, okay, now can you complete this sentence for me? This means that what? I am claiming that this is the true statement. If you say this is not true, then you have to say that this is true. Empty set is not the subset of A. But this means what? Can you just complete my sentence?
It means that there is something in the empty set which is not in set A, but there's nothing in the empty set.
Yeah, thank you very much. Then this means that there is an element X that is an element of empty set, but it is not an element of A. So you see, I am claiming this is the true statement. If you say no, it means that is your responsibility now. You have to find an element which is inside A, inside the empty set. It is a member of the empty set, but it is not a member of A. When you say no, that is your responsibility now to cook up that, to find that element in the empty set. But is it possible that you can find an element in the empty set? The answer is no, because the empty set doesn't have any elements. So it means that because logically, not because of the weakness or whatever, because logically, by definition of the empty set, there is nothing inside the element in the empty set. I cannot find an element which is inside the empty set, and it is not in the set A. Because of this, we have to admit, we have to accept that this is the right statement. Because in the logic that we are talking, either a statement is true or its negation is true. They cannot simultaneously be true or false. This is called the negation of P. So this statement, if you consider this statement P, this is the negation of that statement. It is negation of P. If I am claiming this P is true, if you say no, this means that not P should be true. But the consequence of accepting not P to be true, it means that I should be able to find an element in the empty set, which is a contradiction by the definition of the empty set. So I have to admit this is not the case, so the other one has to be the case. Is that clear?
Yes.
Okay. So number 4 is not that hard, but I want you to practice here as well. So number 4, let me write it in symbolic way. So let A, B, and C be sets such that A is a subset of B and B is a subset of C. We prove that A is a subset of C. How should I prove this? There is one way to show. My goal is to show this. So it means that I should show that whatever is in the left-hand side is also an element of the right-hand side. So I would say that let X be an element in A. Let me write using these mathematical symbols. We show that X also belongs to the right-hand side. If I can show this statement, then I am done based on this assumption. Okay, now can you tell me, I know that X belongs to A, and I know that A is a subset of B. Okay, can you tell me what would be the conclusion here? What can I conclude from these two statements? X belongs to A on the one hand. On the other hand, I know A is a subset of another set called B. What can I conclude about X and B?
X belongs to B.
X belongs to B, exactly. Now I know that X belongs to B. Now We know that X belongs to B, and I have another assumption here. B is a subset of C. So I would say that B, so by the way, if you want, I can write this instead. This comma is a little bit vague, but let me write and here. So X belongs to B, and we know that B is a subset of C. Immediately, you can conclude something similar. X belongs to B. B, on the other hand, is a subset of C, so I can conclude that X belongs to C. And that's the end of the proof, yes? What was my goal? My goal was to show that this X that I have chosen here will be in C. So I did it in two steps. You told me X is in A. Someone tells me that this A is subset of B. So immediately, by definition of a subset, I can conclude that X is in B. This is guaranteed now. If you guarantee this to me, because of this assumption, this is guaranteed now by the definition of being a subset. Now I will take this guaranteed statement and I use the second piece of information that you provided for me and put them next together. And then again, using the definition of the set, I can conclude this last statement. But the last statement is exactly the statement that I wanted to show. So I am done. Okay? So if you want to draw some diagram for this, it's very clear. Yes. So I have a diagram for this. This is the universal set. And then I have a small set here, A. And then I have a little bit bigger set here, for example. And then I have a little bit bigger one. Yes. So it's clear now that if this set is C, this blue one is B, this green one is A. So immediately you see that, and this is U. Immediately you see that A is a part of B, is contained in B. B itself is also contained in C. So it means that it is clear that A is also contained in C. If you want to write it using the rules, so you can write it in this way. So if I have A is a subset of B and B is a subset of C, then if you want to, you can conclude that A is a subset of C. So let me put this in a box. And I know that I had already done this for you. So let me just write it with another red color, which is not correct in general. If A belongs to B and B belongs to C, is there any guarantee that you can conclude that A belongs to C? Do you remember? So in other words, here, this relation is transitive. But now I am asking, do you think the relation of belonging to is also transitive?
No.
No. Do you remember? Can you cook up an example? Let me make it simple. We can cook up an example, by the way, which this one is true. But let us say in mathematics, when we say a statement is false, a general statement is false, it doesn't necessarily mean this is false all the time. It means that there exists a situation for which the statement is false. So when I say this statement is true, it means this guarantees that this statement is true under all conditions if I choose A, B, and C according to these assumptions. But when I say this statement is false, because this means that there exists at least an example that you can come up with so that these two are correct, but this is incorrect. It doesn't necessarily mean that this is always incorrect. So be careful about this point in mathematics. So let me talk a little bit here. So let me cook up an example for which this red one is not correct. Let us make it as simple as possible. So I would write A equal to just simple 1. For B, I would write it as this set. And for C, I would write it in this form. I would write it as this. Yes? This is an example. So let us consider here. For this example, A belongs to B, true or false for this one?
True.
It is true. What do you think about B belongs to C, true or false?
Also true.
This is also true, but what do you think about A belongs to C?
False.
False.
This is false. But now I want to cook up an example for which this is correct. For example, I can just do it in this form. I can keep A as it is. I can write B in this form. But it is clear what to do with C. Yes, I can include B in it. I can also include A in it. Now let us go back again. A belongs to B, true or false? True. B belongs to C, true or false? True. A belongs to C, true or false?
True.
True.
True again. So you see, when I say that this is not correct, it means that I can cook up an example for which this is not true. But it doesn't necessarily mean that it's always false, because you see, at least I cook up an example for which this was right. So let me just put this in a box so you don't need it here, but just want to draw your attention again to this. Don't get confused between this relation of being subset and the relation of being belonged to, okay? So this is it, and then I want just to explain the last statement, but the proof will come later. So what is this tells you? This tells you that if you have a set with n elements, when you say cardinality is n, it means that inside your set you have n elements. If you want to find the subsets of that, let us see what would be this number. Let me give you an example. Might be you can find the pattern yourself, at least you can guess the pattern. Okay, so before finishing that, so let me leave this empty space here. I will come back to it, and let me start an example. So example, write down, this is also in the book, so write down all subsets of the set A equals to A, B, and C. Okay, so what are the subsets here? If you go back here, what is, I would say, I put the smallest in quotation. What is the smallest subset of any set? You understand what is the meaning of a smallest here? The empty set. And then that was the proof. So I go to this statement. So remember that the empty set is a subset of every set. For any given set, what is the biggest subset? Again, biggest in quotation mark. For a set, what is the biggest subset?
Itself.
Itself, yes, exactly. So these are two extreme cases when you want to write down all the subsets of a given set. So what you do, so you start with this list. You write empty set. And the next one, can you tell me, for example, here I have the cardinality is 3. So I can have singletons. How many singletons I can write? 3 of them. One including just A, the other one including just B, the other one including just C. So let me write all of them. So another one is just what? A. Another one is so let me organize them for you. So the first one is empty. There are 3 singletons here. So this is one of them. This is the other one. And this is the other one. Now I will have 2 element sets. One of them contains A and B. the other one contains B and C, the other one contains A and C. But let me ask you a question. Do you write B and A for a new one in this list?
No.
No. Why? Because if you remember,
Doesn't matter how. Yeah.
Yeah, exactly. It doesn't matter.
Doesn't matter. Yeah.
So you should either write AB or BA, but not both. So it's very important to remember when we talk about a set, the elements are not ordered. You can write them in any way that you like, but you are not allowed to repeat that once. So write this one and then write the other one as well. No, just one of them. Is it finished or something is left?
Itself is left.
Itself, and that is the highest one in the hierarchy. So you see, that it is completely clear. I cannot exactly order my subsets. These are not comparable. I cannot say which one is bigger. Bigger means in containing the other one. This does not contain that. This does not contain this. These are not comparable. But any set above is the subset of a set below, of any set below. Yes. If you want, can I compare this? Sorry, this is also not the case. This one and that one are not comparable. You see, this is not a subset of this one. This one is also not a subset of that one. Yeah, so this is not a total order. Some of them are ordered, some of them are not. Okay. But these are the only subsets that I can come up with. How many of them are there? 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so let me just do this quickly for a 4-element set. It might be a little bit boring, but let us just do that. So example, do the previous example for this set. A includes A, B, C, and D, 4 of them. Okay, so what would be the solution this time? Again, the empty set is the smallest one. Okay, and then how many singletons I will have? I will have one singleton A, including only A. The other one is B, the other one is C, and the other one is D. And I can also have 2-element subsets. So here you need to be a little bit organized to make sure that you are not ignoring some of them. So I will do like this. I will take A and I will write it once with B, once with C, once with D. And when I am done, I will go back to B. So it becomes A and B, A and C, A and D. But then I go to B. But be careful, don't write B with A again, because this one is the same as the first one. So I need to write B with the next one, not the previous one. So it becomes B and C, and the next one, so let me just clean this comma, and the next one is B and D. When B is finished, I go to the next element, which is C. But I will not write C with the previous ones, because if I write CB, CB and BC are the same. So it means that I write C and the last one, which is D. Okay, I don't think that there is more of these 2-element subsets. Then I need to go to 3-element subsets. So what are they? Again, you need to be careful. It becomes a little bit tedious work you need to be careful about. So A, B, and C is one of them. Let me keep the first and the second one, but change the third one to the fourth one. So this becomes A, B, D. Can I have more? Yes. It should be the other one, B, C, D. But I hope that you are convinced that there is no more 3-element subset for this set. Yes? Am I right or not?
C, D, A.
Yes, so there are more, yes? So what you said, C, D, A, so let us write A, C, D. Is there any more? Is there? Hello?
I don't think so.
Yeah, there is no. You are right. And so then I go to the biggest one finally with 4 elements. Yes. So here, if you remember, what was the number of subsets is equal to 8. Let me count this one as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so this time the number of subsets is equal to what? 16. Now can you see at least some pattern going on here?
It doubles for every new element.
So meaning what?
That it
If
is,
I have a set with n elements, how many subsets are there? So you see
2n minus 1, to the power of n minus 1, I think.
no, just 2 to power n. Why minus 1? Because
If
here
it has 1, then it doesn't have. Oh yeah,
no,
no,
here
sorry.
no, here we have, because we are counting this one as well, we are also counting the subsets. So I'm talking about all subsets. Yes, so it becomes 2 to power n. This is the formula. If you want to know the number of subsets that you can write for a set, that number is 2 to power n. Okay, so in this case, of course, this is not the mathematical proof, but at least you have the idea what's going on. So this was 3, the number of elements was 2 to power 3, which is 8. Here we had 4 elements, the number was 2 to power 4, which is 16. And this turns out to be the number that I have to go back and put it there. So I would write that if A is a set of cardinality n, then the number of its subsets is equal to 2 to power n. I want you to know about this, but the proof will come later. Okay, let me just mention a definition here. So definition. And by the way, before definition, how many subsets do you expect for the empty set?
1.
That is?
Itself.
That is itself. So you see the number of elements in the empty set is 0. So according to the formula, it should be 2 to power 0, which is 1. So the number of subsets is 1, and that is the empty set itself. Okay, so let me just write this as a remark. This empty set is the only subset of this. Okay, the empty set is the only subset of this. And then, by the way, be careful. Here, you need to choose. Either you can write this in the first, or you can write this. That's also correct, but you are not allowed to write something like this. This is not correct. Be careful about that. I have already talked about this. So let me just introduce you a definition here. Definition. The set consisting of all subsets of a set A is called its power set. And it is denoted by so you have this calligraphic P, it's hard to write, but something like this, and then you have this. Yeah, let me write it easier, because otherwise So let me make the P a little bit bigger like this. So this is called the power set. So in principle, if I want to define a mathematical definition for the power set of A, it contains all sets such that X is a subset of A. So that is called the power set. But the power set is very, very simple idea, because you see, when I was talking about the subsets, I wrote them in an inorganized way. If I collect them into one set, that is called the power set. That's it. So when I say power set, it means that you need to put a curly bracket around them so that they are now seen as the elements of another set. That bigger set, which contains all of these elements, is called the power set of that one. So for example, let me go back here and change my color. So if I want, for example, to write the power set of this set here, you open a curly bracket here. The first element here, I put empty set, I separate it with comma, and then I put this, and then I put B, and I put C here, and then I go to A and B. Hopefully I will have enough space, and then I have B and C, then I have A and C, unfortunately, and then I will have A, B, and C, and then I will close that curly bracket at the end. Yes, so this is just called the power set. So if I ask you to write the power set, you need to respect the punctuation rules. Yes, so it means that not only I am testing your knowledge for being able to write all the subsets, but I also want you to respect the punctuation rules, meaning that you need to have two curly brackets around them and separate all the subsets with an extra comma. Is that understandable?
Yes.
Okay, now can you cook up a formula for the cardinality of this set? So let me write a remark here. Let A be a finite set. Then the cardinality of the power set of A is equal to what?
2 to the power of the cardinality of A.
Exactly. So that's exactly the formula that I wanted to write. Yes, because this is not something very big, but the name is a little bit fancy. So the cardinality of this subset of this set, when I ask you what is the cardinality of this, what I mean is just count the number of elements that you see here. So it becomes 8. But I told you, if you trust me, the formula is 2 to power 3. But what is 3? 3 is the cardinality of A itself, yes? So that is why this formula is correct. The cardinality of the power set is equal to 2 to the power of cardinality of the set itself. Okay? Let me ask your opinion now. Let us do some exercises here. So what do you think would be the cardinality of the empty set? Let me ask you this question first. What is the cardinality of this set? Let us write it. So how should I write it? I need to open a curly bracket here, and I close the curly bracket here. What I need to write inside are all possible subsets of this set that you see here. But according to that theorem, you immediately realize this list starts with the empty. It's not a good way to say start because there is no order, but I'm saying start because I want to have an organized brain to make sure that I'm writing everything. If you write empty in the middle, that's also okay. But then it's not organized way of doing mathematics. Okay, what do you write after that? If you want to have an organized brain, you will write this set with this one and the next one. It's very important now, separate them as with commas. And then this one, and finally the whole itself. So it's very easy, yes? And then again, you can see that it is confirmed that how many subsets did you expect before doing that? because the cardinality here is 2, so 2 to power 2, which is 4. And then you see that you have 4 of them exactly here. Now I am asking you the same question here. What is the power set of the empty set? How do you write it punctuationally correct? Let me ask you one question. Do you think this true statement, true or false?
It's false.
It is false. Okay.
It's the singleton of and then empty set.
Exactly. So they are not the same thing. Thank you very much. So this becomes equal. What is the rule? I need to open a curly bracket and then close it. And what I need to put inside are the subsets of this set that I see here. But if I ask you what is the subset of the empty set, there is only one of them. What is the subset of the empty set? It is the empty set itself. So I need to put it here inside. Is there any more? No, I have to close it. That is the set. So let me write it more properly. So I will write just the empty set here and then close it. Is that understandable? Let me ask you another question. What is P of empty? I want to wait a little bit for you so that you can write this yourself. Okay, and then let me also write this one. I want you to see how do you do that. Okay, but everything should be 100% correct. I just want to wait for a little bit for you. I don't know, I think 2 minutes is enough. Okay, so if I want to do this from scratch, which one I should do first? I need to go to the internal one, yes? I need to do this one, and when I found the answer, I will apply the next power set onto it, yes? But this part is already done here, so I need to put this here, okay? So this was the trivial part, so let me just do it. So this is what I write here. Okay, now Alex, do you want to continue or someone else? I don't know.
Could I take
First of all, let me ask you, Alex. So, okay, so what would be the number of elements that you expect here? So I need to open curly brackets and then close it, and I am supposed to write all the subsets of this. If I ask you how many subsets you can imagine for this, one of them is the empty set, and then the other one, this is a singleton. So there is only another one more, that is this one. These are the only two subsets. Do you understand that? The reason that this is a subset, because I told you that the empty set is the subset of every set that you can imagine. So you shouldn't doubt that I need to put empty set here. That's for sure. And then I told you that the set itself is also a subset of itself. So that's also clear that I have to put this one itself. But is there more than this? No, because this is a singleton. It means that there is only one element there. So the number of subsets is 2 to power 1, which is 2. And I have already written the two of them. So these are the only ones. So this would be the answer to this. So let me make it clear now. So I would write the empty set and the singleton containing the empty set. And then let me now clean this and bring it more close. Okay, before answering the second one, what is the cardinality of this one immediately? Can you tell me by
4.
looking here? It's 4, yes, because this one has already been done and I see that there are 2 elements in it. And then I want to find the power set of this one once more, so it becomes 2 to power 2. The number of subsets are 2 to power 2, which is 4. So I need to expect 4 of them. So again, you see, I open a curly bracket here and close it. I don't know, let me put it farther away so that we have enough space. But again, you see, it is very clear. The list, I can start it with the empty set and I can end it with the set itself. Okay, but there are 2 more here. because I am supposed to have 2 of them. So can you tell me what should I write, for example, here and here? So you need to remember that, so you need to respect the punctuation rules exactly, including the curly brackets, commas, and everything. So what is the next, for example, here that I can put?
The singleton containing the empty set.
Exactly, because this would be the singleton containing the empty set. What is the next one? Again, that should be a singleton again.
The singleton of the singleton of the empty set.
Yeah, exactly. So the singleton containing the singleton of the empty set. And that is the only one that are done. So this is the power set of this set. You are not, so the only thing that you can write different from me is to replace these things if you want to. But the number of curly brackets and whatever I have used, that should be exactly the same thing. You're not allowed to do it something else. Okay. Is that understandable?
Yes.
Okay, so just now I want to tell you that the notion of power set is optional. This is not in the book, but I think it is not something very hard that you don't understand. If you don't understand, if you understand up to here, you don't need to know this up. So let me write optional. Whatever is here is optional. So optional starts from here up to here. Yes. So you don't need to learn this if you don't want to. I will not give any question in the exam regarding this power set, but I think that was also interesting if you see this. So here, I think we can stop here now. Yeah, I think it's better to stop here. Then the next time that I want to teach a new lesson, I will give you another example to refresh your memory. So let me keep this example for the next session, and then I will continue to the next lesson. So before this, we have one session on Monday, so we are not able to finalize set theory. Yes. And we also have another session on next Thursday. So might we will be able to finalize the set theory, and then the next topic of this chapter would be very important, which is combinatorics, and after that it is graph theory. So 2 more topics are left, but these are extremely important. And the next chapter in Math 5 is actually more or less similar to Math 4. So we go and study differential equations. We study differential equations a little bit in Math 4, and then everything is completely ready and we can go and study differential equations in Math 5, which is a little bit more advanced. And the next chapter in Math 5 is actually nothing, there is no lesson there. They have written a lot of examples from practical world so that they want to test your ability with how you can solve the real world problem using the math knowledge that you have gathered up to that point. So I mean that Math 5 is actually, so you need to expect 2 more subjects, combinatorics and graph theory for this chapter. And the next one is goes very smoothly. It's like Math 4, so we need to learn how to solve some differential equations. Okay, so let me stop this video here.